All right, we'll do two examples with electric fields, and really this is a calculus lesson more than anything else. So we would love to be able to use Gauss's law. Love to be able to use Gauss's law to find electric fields. However, Gauss's law needs some symmetry, and it needs things to be infinitely long because it needs the E field to be constant on the surface, right? Gauss's law is really the most popular way to find the E field. And again, that's saying this. But we need to be able to do a surface integral and surround this thing and have equally the E field equally along this area. So we can't use Gauss's law in a situation where, let's say you have this line of charge, okay, and I want to know the E field there. Well, that's a little more difficult, okay, because what Gaussian surface are you going to put around this this just length of, charge of line of charge of length L that you can put around so it's symmetrical so you can take the E field out and do this. So Gauss's law is not going to work on these finite cases. Can't use it. Not that it, is not a true statement, but it's just impossible to get some Gaussian surface to make this happen. So what you have to do is you got to go old school and say something that hopefully is very obvious at this point on your calculus career, is that the E field is the summation of all the little bitty dE's. Again, I know this is some finite object, but what we're going to need to do is we're going to need to break this object up into an infinite number of really small point particles. So we break this object up into really, really small pieces, and we say, well, each one of these pieces has its own E field. And the E field at this point, right, assume this is some positive charge, right? We know that the E field at that point right there is going to be going this way. Right? We know it's all that direction. All of these charges are going to push the E field this way, but that charge and that charge and that charge and that charge, well, they're all different distances from that point. And so their E field contributions are all a little bit different. However, we certainly can say that the total E field is the summation of all the individual E fields. Well, what's each individual E field? Well, we know that the E field due to a point charge is K Q over R squared. In this case, we can't call it Q, Q's being the total charge here, but we can say dQ. Okay, so this thing has a total charge Q, and it has a length L, and so then it has a density, a charge density of Q over L. Again, charge density, this is a linear charge density. This would be in coulombs per meter. And so what we need to do is figure out what dQ is. All right, well, dQ is the small amount of charge, right? This thing right here has a certain charge, and that's dQ. But it also has a certain thickness, dr. And so how is dQ, the charge on that little bitty guy, related to dr? And again, that's where this density comes in. Think about for this for a second. It's really not too hard of a relationship. dQ is equal to Q over L times dr. The charge on that guy is equal to the charge density, coulombs per meter, times meters, which is the thickness of that particular little bitty segment. Again, if you take a density, a linear density, times the length, then you get the charge on that particular piece. Then I can make that substitution in here. So then instead of dQ, I can write it's Q over L dr over R squared. And now I can accumulate that. Okay, let's give me some distances here. This we said was length L. Let's say that you're looking at a point in space d away from the end of one of those things. Okay, and so what are we going to let R vary from? Well, think of this segment. How far is it away from here? Well, it's d away. Well, how far is this guy away? That little bitty charge, that little bitty t away, well, that's all the way at d plus L. So our R value is going to vary from being d away to d plus L away. So those are our bounds here. I'm not going to do the integral yet, I'm just going to factor out the k, the q, and the l, because those are all constants. kq over L, I'm still going to integrate from d to d plus L of dr over r squared. Okay, the integral of that is k, q, L, and the integral of 1 over r squared is negative 1 over r, and we got to evaluate from d to d plus L. Okay, so that's k, q, L. I'm going to put that negative over here, so that's negative 1 over d plus L, and then a minus is going to be a plus 1 over d. Okay, now I'm going to multiply top and bottom here by d. So make that a d, put a d up there, and then multiply top and bottom here by d plus L, and top and bottom here by d plus L. And again, all I'm doing is adding and subtracting fractions. So this denominator is d plus L, and look up top, you gotta look here real carefully. This is a minus d plus d plus L. So that minus d and that d cancel, and so the numerator is just L. So this was kq over L, and then this thing is L over d times d plus L. And if I lost you on that, well, go slow and it's just fractions. I just added fractions and I cancel it right. The numerator had some terms that were the same, and then those L's go away, and then you're done. The E field is equal to k, q over d times d plus L. And it actually even makes sense, because if d is much bigger than L, what happens in the calculus world? Well, in the calculus world, if d is much bigger than L, then we can ignore this L. And so in this red world, if we're way away, then what does it look like? And it looks like kq over d squared, which is a point charge, right? If d is much bigger than L, meaning you're way away from this thing, then this finite line of charge ends up looking like a point charge. Looks like a point charge. Follows that same format. Now, if you're close to it, well, then this L plays a role in the electric field, and certainly the electric field points to the left. If we were, over here, it would point to the right. Okay, so again, this is doing more of the calculus. This step is hopefully very obvious, but obviously it's also the most important step, is to say what? That the E field is the accumulation of all the individual E fields. Each individual E field is just a point charge. So we're going to take this line and break it up in an infinite number of little bitty segments, and each segment has its own E field, k dq over r squared. We write dq is the density times the thickness. So we take the little bitty charge and then rewrite it as part of a little bitty length, and then we can integrate over the lengths. Okay, I'm going to do one more. So this was the finite line, and now I'm going to do a hoop. Okay, so same procedure, except I'm going to do a ring of charge. This one's really hard to draw. So when you imagine you have some ring, and this one's hard for me to draw, and the ring is centered on this axis. So this line goes through the center of this ring. So this is on the outside, and this is on the back side of this line, and this line is right on this center. Okay, so let's say I was interested in the electric field right here. Okay, so I'm on the center of the axis, but I'm a distance away from it. So if this is kind of the center, okay, that's the radius, which is some capital R, and then this distance is x. That's how far I am away from the center of this ring of charge. Okay, first of all, what direction is the E field? Well, you can think about all these different contributions. So some of the charge is located up here. Okay, so let's look at this little bitty red segment here. What direction is it, that part of the ring, what direction is it going to push? Well, it's going to push the E field that way. Well, what about the symmetrical piece down here? That little part of charge, well, that's going to push it this way. okay? If you thought about this piece, that's going to actually push it into the paper, but then that piece right there is going to push it like this, out of the paper. All of those things make it so that the E field is pointing to the right. So we actually know that at that point, the net E field, which is the sum of all the E fields, is going that way. And all of these things have a certain angle with them, right? They all have some random angle that we need to get. This angle here is just some we really just need that piece, right? So we're gonna have to introduce some cosine. And we end up doing the same thing we did before. The E field is the accumulation of all the DEs, the magnitude of all the little bitty things, but we have to multiply by a cosine theta because we need the horizontal component of all of these guys. We only need this piece. We can't use all of that because all of that, we know that all the vertical pieces are going to cancel with that, with the opposing of other vertical pieces, and all these horizontal pieces are going to add up. So this is me saying we know that the E field is only in the x direction, and that we're going to sum up all the contributions, but we need to multiply by cosine theta. Okay, same thing as before. We know that the electric field is just the summation of all these little bitty electric fields, right? All of these parts, every single part of this ring of charge has its own contribution, and they are K times dq all over r squared cosine theta. Okay, and now let's draw that triangle. Okay, this distance is r, this distance is x, and this is cosine x, or excuse me, that's theta, and that's little r. Little r being, okay, right, remember, this is the part of the ring we're looking at. It's right here, and it's going to this point. So little r is the distance my dq is from the point I'm interested in. So what is little r? Well, little r is then the square root of x squared plus r squared. And what's cosine theta? Cosine theta, cosine is adjacent over hypotenuse, which we can write as x over the square root of x squared plus r squared. Okay, so let's make some substitutions. Okay, don't mess with the dq, and I can explain why in a second, why we don't need to do anything with the dq yet. K dq over r squared. This squared just gets rid of that square root, and then cosine is x over the square root of x squared plus r squared. Okay, here's the best part of this. Do you see how every one of these things, every one of these points on this ring is actually the exact same distance from this point, right? That distance, and that distance, and that distance, they're all the same. Remember, this ring is just vertically going through this paper, and so this point is the same distance from all these spots. So this little r is not some function, it's a constant. X squared plus r squared is a constant. And so k, x, r are all constants. They can all be factored out. K, x, and then this is x squared plus r squared times another x squared plus r squared to the half power. So that's x squared plus r squared to the 3/2 power, right? This is 1, which is two halves. Another half is 3/2. And then integrating, and the only thing left in here is dq. Well, what happens if you accumulate all the dq's? Well, you just get q. So we get k q x over x squared plus r squared to the 3/2. And we have the electric field. We have the electric field due to a ring of charge. Again, the given information here was that the ring had a total charge q and had some radius r, and we were looking for the electric field at distance x along the axis of that ring. All those things are important. Okay, and then what we can do the same thing. What happens if we look at the limit of the E field if we let x get big? Which is the same thing as some people in physics would say, okay, let's let x be much, much bigger than r. Again, if x is much, much bigger than r, then this goes away to 0, and then you get x squared to the 3 halves, and so you get k, q, x. X squared to the 3 halves is just x cubed, which is then k, q over x squared. And you're like, oh, cool, that makes sense. Because eventually, if I had a ring of charge and I got far enough away from it, then it really shouldn't look like a ring anymore. It should just look like a point charge, and then it should act like a point charge, kq over r squared. Or x is pretty much, if you get far enough away, this ring, so like think of the ring as really, really, really a tiny ring, and now you're way away from it, then that ring is pretty much just a point charge. And then we know the electric field looks like this. So this actually makes sense if we look at the limiting cases. And again, a calculus person would say, let's look at the limit of the E field as x gets really, really big. And then someone else might say that x just needs to be much, much bigger than r. And so then we can get rid of this r squared, because x squared is way bigger than r squared. So x squared plus r squared is pretty much just x squared. Okay, those are kind of the two cases that we really need to use. This idea here that we can't use Gauss's law. And again, really what I was saying here in all these cases is that for some finite thing, the electric field is just the summation of all the individual parts, and we have to break it up. The first one we broke a line up, and here we're breaking a ring up, and then this one we need to do a little geometry and a couple of relationships. And the other one we actually had to go, I thought was a little harder, because you have to write dq in terms of dr. And then you actually have to do a hard integral here. The integral is just dq, which is just q. Okay, so these are your two cases. These are the most popular cases that you'd be responsible for, kind of using the calculus to look at the electric field due to some finite structure.